You know, usually when we talk about a medical diagnosis or like understanding our physical world, there's this expectation of mechanical precision,
Right.
right?
Yeah, absolutely.
Like you break your arm, you get an x-ray and it shows that jagged white line and the doctor just points at it and says, there it is. It's totally binary. It's broken or it's not broken.
And we really crave that, don't we? I mean, we like our problems to be highly visible. We want them easily categorized and just entirely distinct from the background.
Exactly. But then, and this is what's so wild, you step into the world of our own biology and our environment, and suddenly that x-ray machine is just utterly useless.
Yeah, it just doesn't work.
We're looking at a landscape that is murky, and
Yeah.
it's murky precisely because the single most important substance to our survival is, well, it's something we look right through every single day.
Literally look right through it.
Right. We assume it's passive. We just assume it's the empty space in the glass.
Which is pretty much the absolute definition of hiding in plain sight,
So, welcome to today's deep dive. If you are listening to this, you are looking for the why and the how, not just a list of dry facts. Today, we are opening up an incredibly dense, really fact-packed piece of academic research.
Oh, it is dense.
Yeah, it's titled 141145.pdf in our source stack. And it is basically a complete deconstruction of water.
Down to the atoms.
Exactly. But our mission today is to fundamentally change how you view that simple glass of water sitting on your desk. And I want to jump straight into a statistic from this research that honestly, it completely reframed this entire topic for me. It's like the ultimate lens for everything we're about to discuss.
It really sets the stakes, I think, for the entire conversation.
It really does. So the human body, your body, my body, the brain that is processing these words right now, it consists of about 70% water.
70%, yeah.
Biologically, we are essentially walking, talking bags of specialized fluid. But out of all the water on planet Earth, only a minuscule 0.2% is actually fit for us to drink.
It is a staggering vulnerability, really, when you stop and actually process those two numbers side by side.
I mean, 70% versus 0.2%?
Right. You have this terrestrial organism, a nasus, obviously, that is entirely dependent on a highly specific chemical compound. We need it for our very cellular structure, for nutrient transport, temperature regulation.
Pretty much everything.
Everything.
Mm-hmm.
And yet, the usable, accessible supply of that precise compound on the surface of our planet is, statistically speaking, it's a rounding error.
And this is exactly why you're here to guide us through this material. Because if we are 70% water and we only have access to 0.2% of the Earth's supply, I look at that and just think, how does the math on our civilization even function?
Well, it functions very precariously. And to understand that precarity, we really have to start by zooming all the way out.
Okay.
We have to map out where the other 99.8% of the water actually is. Because that 0.2% number sounds almost like a typo.
Yeah.
Until you actually break down the global distribution.
Okay, let's unpack this. Because you look at a globe, right, and it's mostly blue. So the immediate intuitive thought is just, oh, we live on a water planet. We have boundless resources.
Water everywhere.
Right. But if we look at the scarcity like a financial budget, it paints a very different picture. Imagine you have $1 million to your name, but almost all of those accounts are just completely frozen, locked away in trusts you can't touch, or held in currencies you literally can't spend.
That's a great way to look at it.
You basically have to survive the rest of your life on the loose change you found in your couch cushions.
And that is exactly our species' relationship with water. According to the breakdown we're looking at today, 97% of the Earth's water is in the oceans.
So 97% of your total wealth is just immediately inaccessible.
Immediately. Because of the dissolved salts, obviously.
Right.
The marine environment thrives on it. But for terrestrial mammalian life like us, and for the agricultural crops we cultivate to survive, that 97% is biologically useless.
Because it's toxic to us.
Exactly. If you try to irrigate a field of wheat with ocean water, the high concentration of sodium and chloride ions will actually pull the moisture right out of the plant's roots.
Oh, wow. Through osmosis.
Through osmosis, yeah, and effectively dehydrates the plant to death. And the exact same thing happens in the human body. Your kidneys just cannot process that level of salinity without drawing more water out of your cells than you are actually taking in.
So drinking it actually accelerates your own dehydration.
It does. It kills you faster.
Okay, so 97% is completely off the table. We are left with this tiny 3% sliver of the global budget. But the breakdown in the text gets even more restrictive, doesn't it?
It does, yeah.
Because of the total water on Earth, 2.1% is locked up in glaciers and ice caps.
Right, so this portion is technically fresh water. It doesn't have the salinity problem of the oceans.
But it's ice.
It's ice. It presents a massive logistical and physical barrier.
Yeah.
It is frozen solid at the poles, in Antarctica, Greenland, or sitting at the very top of alpine mountain ranges.
Right.
So it is just completely inaccessible to the vast majority of human population centers.
Yeah, I mean, we can't exactly run a pipeline from a glacier to a city in the middle of a desert, so that leaves us with just 0.9%. And the research then notes that 0.6% is groundwater.
Which is hidden beneath the surface. Now, groundwater is incredibly important, obviously, but it requires mechanical extraction.
Like wells and deep drilling.
Exactly. Wells, pumps, drilling down into aquifers. And aquifers are essentially these porous rock layers underground. But the problem with groundwater is that it doesn't replenish quickly.
Right. It takes time.
A lot of time. It can take centuries or even millennia for rainfall to slowly percolate down through the bedrock to actually recharge a deep aquifer.
Wow. Millennia.
Yeah. And as we'll explore a bit later, because it's sitting right beneath our civilization, it is incredibly vulnerable to the chemical runoff of, well, basically everything we do on the surface.
And we are still whittling down the budget here. There's another fraction mentioned in the text, 0.001%, which is atmospheric water vapor.
So, the humidity, the clouds you see in the sky.
Right. It's a vital part of the water cycle, obviously, but it's transient. I mean, you can't turn on a tap and just draw from a cloud.
No, you can't. Which leaves us with the final number.
The loose change in the couch cushions.
Exactly. Only 0.2% of the total water on Earth is inland, liquid, fresh water. The rivers, the lakes, the streams, the reservoirs.
That is the potable water. That is the 0.2% margin that literally sustains every city, every farm, every terrestrial ecosystem.
And that tiny, tiny fraction is exactly why our source material opens with such a stark, urgent warning about pollution.
Yeah, the warning at the beginning really sets a tone.
Because that 0.2% isn't just sitting safely in some vacuum. It is the exact same water that flows through our heavily industrialized world. The research explicitly notes that since World War II, we have seen an explosive, unprecedented production and widespread use of synthetic chemicals.
Right. We're talking about fertilizers and pesticides washing off millions of acres of agricultural land every single time it rains.
Every time.
And heavy industrial discharge from manufacturing plants. And the chemical leachate slowly seeping out of municipal waste dumps and landfills directly into that 0.6% groundwater we just mentioned.
Yeah. When you realize that the entirety of human progress, like our food supply, our sanitation, our drinking water, is basically fighting over 0.2% of the globe's water, the introduction of post-World War II synthetic chemicals into that specific supply chain changes the stakes entirely.
It's terrifying.
It is. Currently, waterborne toxic chemicals pose arguably the greatest environmental threat to our urban supplies.
The research makes it so clear, too. The use of polluted water is a fundamental concern for every single person because the scarcity is what makes the pollution an existential crisis.
Right, you can't just pivot to a backup supply.
Exactly. We don't have the energy grid required to desalinate the 97% ocean on a global scale. And we definitely can't melt the 2.1% locked in glaciers.
We are entirely tethered to the 0.2%.
Which honestly forces us to ask a much deeper question here. If our survival and the survival of the entire biosphere we rely on is so completely dependent on this one specific liquid, we really need to understand what makes it biologically and physically irreplaceable.
Why water, right?
Yeah, why water? Why not liquid methane or ammonia or literally any other compound? To answer that, the research pulls us out of the macro global scale and drops us right down to the microscopic molecular level.
And this is where the sheer physics of water reveal themselves to be incredibly anomalous. I mean, water breaks so many of the standard rules of chemistry and physics that apply to almost every other substance on Earth.
So let's talk about these physical marvels. The research outlines the basic composition first. 2 parts hydrogen, 1 part oxygen. Pure water is clear, colorless, odorless, and tasteless. It is neutral to litmus, meaning it's perfectly balanced. It's neither an acid nor a base.
Which, sounds incredibly mundane on paper.
It really does. It sounds like the baseline default of the universe. Like its freezing point is exactly 0 degrees Celsius and its boiling point is exactly 100 degrees Celsius at sea level.
And those numbers are so deeply ingrained in us because they are the literal anchor points for how humanity measures temperature in the metric system.
Right, Celsius.
Yeah, Anders Celsius essentially looked at water and said, okay, this is the most important substance in the world. Let's build our entire concept of thermal measurement around its phase changes.
But then the research throws in a very specific, highly unusual density metric. It states that the maximum density of water is 1 gram per cubic centimeter. But here is the catch. It hits this maximum density at exactly 4 degrees Celsius, not 0. 4 degrees.
And this is the first major rule that water just completely breaks. This is a profound physical anomaly.
Okay, walk us through why 4 degrees is such a massive deal. Because intuitively, things get continuously denser the colder they get, right? I mean, that's just physics.
Exactly. That's how it normally works. With almost every other substance in the universe, as you remove heat energy like as it gets colder, the molecules slow down.
Right.
And because they are moving less energetically, they pack closer and closer together. The substance becomes denser and it gets heavier. And this continues right up until it freezes solid, at which point it is at its absolute densest.
So like solid lead is denser than liquid lead.
Yes.
Yeah.
Solid iron is denser than molten iron. It's a universal rule.
But water doesn't do that.
No, water does not. Water follows that rule as it cools down from room temperature, sure. It gets colder, the molecules slow down, and it gets denser. But when it hits exactly 4 degrees Celsius, the trend just stops.
It just stops.
At 4 degrees, liquid water is as dense and heavy as it will ever be. As it continues to cool down further to 3 degrees, 2 degrees, 1 degree, and finally 0 degrees, where it actually freezes into ice, it actually reverses course.
That's so weird.
It becomes less dense. It expands.
Which is the mechanical reason why ice floats on top of liquid water.
Yes. And while we take floating ice for granted in our daily lives, like in a glass of water, you really have to understand how bizarre that is chemically.
Right, because the solid state is lighter than the liquid state.
Exactly. If you threw a chunk of solid iron into a vat of liquid iron, it would sink like a stone. But solid water floats on liquid water.
So what is physically happening at the molecular level between 4 degrees and 0 degrees to cause that expansion? Like, why do the molecules suddenly decide to push away from each other?
Well, it comes down to the shape of the water molecule, which we'll get into more deeply later. But essentially, water molecules have very strong magnetic attractions to one another called hydrogen bonds.
Okay, hydrogen bonds.
Right. When water is warm and sloshing around, those molecules have enough thermal kinetic energy to sort of slip and slide past each other, packing in really tightly. But as the temperature drops below 4 degrees, they lose that kinetic energy.
They slow down.
They slow down so much that the hydrogen bonds just take over completely.
Like magnets clicking into place when they start moving?
Exactly like that. And because of the specific angle of the water molecule, when those magnetic bonds click into place to form solid ice, they force the molecules into a rigid, open, hexagonal crystal lattice.
Hexagonal, so like a honeycomb.
Yes, exactly. And that specific hexagonal structure actually requires more empty space between the molecules than when they were just in a chaotic liquid state.
So the structure itself forces them to spread out.
Yes. They arrange themselves into a microscopic scaffolding that takes up about 9% more volume, which means the ice is 9% less dense than the liquid water beneath it.
So it floats.
So it floats.
But let's take this out of the laboratory and put it into the real world. Why does this 4-degree anomaly matter to that 0.2% of inland water we actually rely on? What happens to a lake in the winter because of this?
Oh, this is where physics literally creates biology.
Really?
Yeah. Imagine a deep freshwater lake in November. The air temperature drops below freezing. The water at the very surface cools down. And as it cools, it gets denser and heavier.
Right, down to 4 degrees.
Yes. But initially, because it's heavier, it sinks to the bottom, pushing the warmer water up to the surface. This creates a continuous churning effect called lake turnover.
So the whole lake is mixing itself as it cools.
Exactly.
Oh.
But eventually, the entire lake reaches that magic number, 4 degrees Celsius.
Okay.
The entire body of water is now at its maximum density. Now, as the freezing winter air continues to cool the surface water down to 3, 2, 1, and 0 degrees, that surface water is no longer getting heavier, it's getting lighter.
Oh, so it stays on top.
It stays right on top, it stops sinking, and it freezes into a sheet of ice exclusively at the surface.
And because the ice is floating on top, it acts like a giant thermal blanket.
Precisely. It insulates the rest of the lake from the freezing air above. The water beneath the ice remains liquid, hovering right around 4 degrees Celsius all winter long.
That's amazing.
If water behaved like every other substance, if it kept getting denser until it froze, the freezing water would just constantly sink.
And the ice would build up from the bottom.
From the bottom of the lake all the way to the top, the entire lake would freeze completely solid.
Yeah.
It would kill every fish, every plant, every amphibian, every microorganism.
Every single winter, every freshwater ecosystem on the planet would just be sterilized.
Yes, life in lakes and rivers simply could not exist outside of tropical zones. The 4-degree anomaly is a physical quirk that effectively saves terrestrial aquatic biology every single year.
That is just incredible. But this thermal protection isn't just limited to local lakes freezing over, is it? The research highlights another physical property that dictates the climate of the entire planet.
Yes, it does.
Here's where it gets really interesting. It points to water's exceptionally high heat capacity. It gives a very specific thermodynamic value, 4.2 joules per gram per Kelvin. And it explicitly notes that this is about 6 times greater than the heat capacity of rocks.
This is the planetary thermostat.
I want to break down that 4.2 joules number because, it's really easy to read a metric like that and just nod along. But what is the mechanical reality of a heat capacity that is 6 times greater than rock? How do we visualize that energy transfer?
Okay, think about a hot, cloudless day at the beach in the middle of August.
Okay, I'm there.
You take your shoes off and you walk across the dry sand. Now, sand is essentially just crushed rock. The sand is blistering hot. It's so hot it physically burns the soles of your feet, right?
Yeah, you have to sprint to the water line.
Exactly.
All right.
But when you finally step into the ocean, the water is cool, it's refreshing, maybe even shockingly cold.
Right, but both the sand and the water have been sitting under the exact same sun, absorbing the exact same solar radiation for the exact same amount of time.
Exactly. They're receiving equal energy. So why is the sand 100 degrees while the water is only 65 degrees? It comes down to that specific heat capacity. Heat capacity is basically a measurement of how much thermal energy it takes to raise the temperature of a substance. Because water's heat capacity is 4.2 joules, which is 6 times greater than the sand, it literally takes 6 times more solar energy to raise the temperature of the water by 1 degree than it takes to raise the sand by 1 degree.
So water is just aggressively stubborn about changing its temperature.
Very stubborn.
But why?
Mechanically, what is the water doing with all that solar energy if it isn't getting hotter?
It goes back to those magnetic hydrogen bonds we just talked about.
Oh, the sticky magnets.
Right. Temperature is simply a measurement of kinetic energy, how fast the molecules are jiggling and moving around. When the sun hits the sand, the silica molecules immediately start vibrating violently. They get hot fast.
Because they're not holding on to each other as tightly.
Exactly. But when the sun hits the water, the heat energy has to work incredibly hard just to stretch and bend those sticky hydrogen bonds holding the water molecules together.
I see. The energy gets absorbed into the bonds themselves, rather than immediately increasing the speed of the molecules.
It's like pushing a car with the parking brake on. You're applying a massive amount of energy, but the car just isn't really moving much.
That's a great analogy. Water absorbs heat incredibly slowly. And critically, it also releases heat incredibly slowly. And the research explains exactly why this matters globally. It states this specific property is responsible for keeping the Earth's temperature within limits.
The text actually says that without it, daytime temperatures would be too high to bear, and nighttime temperatures would be too low to freeze everything.
Right. If you look at a planet like Mars, or even our own moon, which lack oceans, the temperature swings are violent. The side facing the sun boils, and the side facing the dark space instantly freezes.
Wow.
Earth doesn't do that because 97% of its surface is covered in this massive thermal battery. During the day, the oceans absorb absolutely immense amounts of solar radiation without drastically rising in temperature.
So it prevents the atmosphere from cooking us alive?
Exactly.
And at night?
At night, when the sun goes down and the atmosphere begins to rapidly cool, the oceans slowly release all that stored energy back into the air. They radiate the heat out, acting like a planetary radiator, preventing the air temperature from plummeting into a deep freeze.
So those 4.2 joules per gram aren't just an abstract chemistry number. That specific capacity is the invisible shield that stops the Earth from turning into a lifeless, scorched rock during the day and an icebox at night.
It is the buffer that makes our climate survivable.
So we have water acting as a thermal buffer, and we have water protecting aquatic life through the 4-degree density anomaly. But the physical marvels in this research don't stop there.
Not at all.
It brings up a third physical property, high surface tension, and it connects the surface tension directly to a biological process called capillary action.
Yeah. If heat capacity regulates the climate, Capillary action regulates the terrestrial food chain.
The research defines capillary action as the process by which water rises up from the roots of plants to their leaves, and it makes a very definitive statement. This process is vital for the survival of land plants.
Let's visualize the scale of what is actually happening here because it is mechanically mind-bending.
Okay, lay it on me.
Imagine a massive California redwood tree stretching hundreds of feet into the air. Now, a tree doesn't have a mechanical pump. It doesn't have a beating heart to pressurize its fluids and push them upward against the immense force of gravity.
So how does a drop of water travel from the dirt, 300 feet straight up into the air, to reach a leaf?
It relies entirely on the physical properties of the water itself, specifically cohesion and adhesion.
Cohesion and adhesion.
Right, because water molecules are polar, because they act like those little magnets we talked about. They love to stick to each other. That's cohesion. It's why water forms rounded droplets on a windshield instead of spreading out completely flat.
Oh, because the molecules are pulling inward on each other?
Exactly, creating a tight surface tension.
But they don't just stick to themselves, right?
No, they also stick to other polar surfaces. That's adhesion. Inside the trunk of that redwood tree, there are microscopic tubes called the xylem, which are part of the plant's vascular system. The walls of the xylem are made of cellulose, which water absolutely loves to stick to.
So what happens inside that microscopic tube?
The water molecules attach themselves to the walls of the xylem tube. They physically grab onto the sides and pull themselves upward to form a tiny curve, which is called a meniscus.
Okay.
But because the water molecules are also holding tightly onto each other through cohesion, when the top molecules pull themselves up the wall, they drag the molecules beneath them up as well.
It's like a microscopic bucket brigade.
It's a continuous, unbroken chain of water molecules extending from the deep roots all the way to the highest canopy. As the sun evaporates one single water molecule off a leaf at the very top of the tree, it pulls the next molecule up to take its place.
And because the entire column of water in the trunk is linked tightly together through those cohesive hydrogen bonds, that tiny pull at the top leaf translates all the way down, yanking another molecule out of the soil at the roots.
Exactly.
Yeah.
The water is literally pulling itself up by its own structural integrity.
Yes. The high surface tension creates a negative pressure system that defies gravity. Without this specific physical property, no plant could grow taller than a few inches off the ground.
Wow.
The entire terrestrial ecosystem, forests, agriculture, the oxygen production of plants, is reliant on the simple fact that water is sticky. That is just, it's a completely different way to look at a forest. You're not just looking at wood and leaves. You're looking at millions of miles of microscopic water chains pulling themselves upward against gravity.
And all of that, the thermal buffering, the ice floating, the capillary action, all of that is strictly the physical behavior of water.
Right, we haven't even touched the chemistry yet.
Not even close. While the physical properties protect the climate and allow plants to drink, it is water's chemical properties that make our own internal biology and the transportation of nutrients possible.
Which transitions us seamlessly into how water interacts with other substances on a chemical level. The research gives water a very heavy, prestigious title: the universal solvent. It claims that given enough time, water can dissolve almost all minerals.
You know, universal solvent is a phrase that should command a lot of respect. It implies a relentless, inexorable chemical aggression.
It sounds kind of scary.
It kind of is. It means that water doesn't just sit there. It actively deconstructs the world around it.
And the research attributes this destructive solvent power to two unique properties. The first is the polarity of the water molecule.
Right. This is the absolute foundation of water's chemical power. Polarity is the engine of the universal solvent.
The research explains this polar nature very clearly, but I want us to really break down the mechanics. It says a water molecule has a polar structure, meaning one end of the molecule has a partial positive charge, while the other end has a partial negative charge.
Yeah.
And it states this happens because of an electronegativity difference between the oxygen atom and the hydrogen atoms. What does that actually mean inside the atom?
Let's visualize the atomic structure.
Yeah.
You have one oxygen atom bonded to two hydrogen atoms.
Oh, yeah, H2O.
A chemical bond is essentially the sharing of electrons. The atoms are holding hands by sharing these negatively charged particles. But they do not share them equally.
Why not?
Because of the protons in their nucleus. The oxygen atom is massive compared to the hydrogen atoms. Oxygen has 8 protons in its center, which carry a positive charge. Hydrogen only has one tiny proton.
So oxygen has 8 times the pulling power.
Exactly. Oxygen is an electron hog,
Mm.
a total hog. That's what high electronegativity means. The 8 protons in the oxygen nucleus exert a massive magnetic pull on the shared negatively charged electrons, yanking them away from the hydrogen atoms and keeping them closer to the oxygen side of the molecule most of the time.
So the electrons are spending all their time hanging out around the oxygen.
Yes. And because electrons are negatively charged, the oxygen end of the water molecule develops a distinct partial negative charge.
Which leaves the hydrogen ends exposed.
Right. Their single protons are basically left out in the cold, so the hydrogen ends of the molecule develop a distinct partial positive charge.
And this creates the magnet. Every single microscopic water molecule has a positive pole and a negative pole, just like a tiny battery.
And that polarity is exactly how it dissolves things. The research states that all other polar substances are soluble in water.
Okay.
The positive end of an introduced substance is attracted to the negative oxygen end of the water, and the negative end of the substance is attracted to the positive hydrogen end of the water.
What fascinates me here is the sheer, brutal, mechanical force of this process.
Oh yeah, it's violent on a microscopic scale.
The research notes that the electrostatic attractions among the ions of a solid salt are overcome by the ion dipole forces of attraction between the ion and the water molecules.
It is quite literally a molecular tug of war.
Let's walk through an example. The research lists sodium chloride as a soluble salt, so table salt.
Okay, take a solid grain of sodium chloride. In that crystal, you have positively charged sodium ions and negatively charged chloride ions.
Right.
And they are locked tightly together in a rigid, alternating three-dimensional grid. Positive, negative, positive, negative. That electrostatic bond between them is incredibly strong. That's why a grain of salt is a hard, solid rock.
But then you drop that rock into a glass of water.
And the water molecules immediately attack the surface of the salt crystal. The water molecules align themselves based on their polarity. The partially negative oxygen ends of the water molecules are magnetically drawn to the positively charged sodium ions on the edge of the crystal.
They swarm it.
They swarm it. Dozens of water molecules grab onto one single sodium ion. Their collective magnetic pull, which is the ion dipole force, is stronger than the bond holding the salt crystal together.
Wow.
They literally rip the sodium ion out of the rock.
And simultaneously.
Simultaneously, the partially positive hydrogen ends of other water molecules swarm the negatively charged chloride ions. They grab onto the chloride and violently pull it away in the opposite direction.
The research describes the aftermath perfectly here. It says the positive and negative ions are pulled apart, and ultimately these oppositely charged ions are surrounded by water molecules, thus separated and kept in solution.
It traps them. It rips the crystal apart piece by piece, and then the water molecules form a cage around each individual ion, pointing their magnetic ends inward to neutralize the charge.
Like a tiny prison cell.
Exactly. Once caged, the ions can't find each other to reform the salt crystal. They are suspended in the fluid. That is the mechanical definition of dissolving.
It's an incredibly aggressive process. But wait, I want to push back on something here.
Go ahead.
If water is this aggressive universal solvent that uses its molecular magnets to rip apart chemical bonds, why doesn't it dissolve absolutely everything? Like, why doesn't it dissolve the plastic pipes carrying it to my house? Or the glass I'm drinking it out of?
That's the perfect question because it reveals the limitation of the solvent. The tug of war only works if there's a rope to grab onto. It relies entirely on magnets.
And not everything is magnetic.
Correct. The research explicitly lists things that do not dissolve in water, specifically mentioning covalent nonpolar substances like benzene, ether, and octane.
Why is a molecule like octane immune to this molecular swarming?
Because octane is nonpolar. The atoms inside an octane molecule share their electrons perfectly evenly. There is no electron hogging.
So no positive or negative ends.
Exactly. There are no partial positive or partial negative charges anywhere on the surface of an octane molecule. It is electrostatically neutral.
It basically has no handles.
It has no handles. So when the highly polarized water molecules bump into the octane molecule, there is absolutely no magnetic attraction. There's nothing for the water to grab onto.
But if there's no attraction, why do they actively repel each other? I mean, why do oil and water separate so violently into different layers? Why don't they just sort of mix together neutrally?
Oh, this is a massive misconception.
Really?
Yeah. It's not that water repels oil. It's that water molecules are so intensely attracted to each other that they simply squeeze the oil out of the way.
Oh, wow.
Think of the water molecules like a crowd of people fiercely clinging to each other's hands.
Yeah.
The octane molecule is a person trying to walk through that crowd, but they refuse to hold anyone's hand.
Okay, I see.
The crowd doesn't push the person away. They just refuse to break their own grip on each other to let the person in. Because breaking a water-to-water hydrogen bond requires energy, and there is no electrostatic payoff to bond with the neutral octane molecule, the water molecules just stick together and force the oil to the surface.
They exclude it through their own internal cohesion.
Yes, and this nonpolar exception is actually crucial for biology. Our cells are surrounded by lipid bilayers, which are essentially membranes made of fats, which are nonpolar.
Oh.
If water dissolved nonpolar molecules, the 70% of water inside our bodies would instantly dissolve our cellular walls, and we would basically just melt into a puddle.
Well, that's a terrifying thought. Okay, so polarity perfectly explains how water rips apart inorganic ionic salts, like sodium chloride. And it explains why it ignores nonpolar fats and oils. But biology isn't just salt and fat.
No, it's not.
What about complex organic materials? How does water dissolve the sugar in your morning coffee? Or the glucose in our blood?
That requires a much more complex interaction, which brings us to the second unique chemical property highlighted in the research. It goes beyond simple positive and negative polarity and dives into the exact geometrical architecture of the water molecule.
The 104.5-degree secret.
Yes, the extensive hydrogen bonding network.
The research gets incredibly specific about the physical shape of water here. It states that the oxygen and hydrogen atoms do not sit in a straight linear line. Instead, there is a precise 104.5-degree bond angle between the two hydrogen atoms.
Right. It's not a straight line like carbon dioxide. It looks more like a boomerang. The oxygen atom is the vertex, and the two hydrogen atoms branch off at exactly 104.5 degrees.
What dictates that specific angle? Like, why 104.5?
It's due to electron repulsion. Oxygen has two pairs of electrons that aren't bonded to anything. They're just floating on the top of the oxygen atom.
The lone pairs.
The lone pairs. Electrons are negatively charged, so they fiercely repel each other, and they repel the electron bonds holding the hydrogens. These two lone pairs push down on the hydrogen atoms, forcing them into that specific cramped 104.5-degree V-shape.
And because of that very specific shape, the research notes something incredible. It says that because of the two positive hydrogen bonds and the two negative lone pairs on the oxygen, one single H2O molecule can form hydrogen bonds with 4 other H2O molecules simultaneously.
Yes, it has 4 distinct docking stations. 2 positive, 2 negative.
And it states that they arrange themselves in a tetrahedral shape around the central water molecule.
A tetrahedron is essentially a 3-dimensional pyramid with a triangular base. So you don't just have water molecules floating randomly. You have one central molecule locking onto 4 surrounding molecules, pushing them out in 3-dimensional space.
Okay.
And each of those 4 is locked onto 4 more, and so on.
So it basically creates a massive microscopic scaffolding. It's a highly structured, interconnected, 3-dimensional web of magnetic attraction.
And this tetrahedral scaffolding is the ultimate bridge between the inorganic world and the organic, biological world. We saw how the simple tug of war rips apart salt. But this complex 3D web is how water interacts with organic life.
The research explicitly says this unique behavior enables water to dissolve many polar non-ionic compounds that contain a hydroxyl group, an OH group. It lists alcohols, organic acids, and most importantly, glucose and sugar.
Glucose, the fundamental carbohydrate, the energy source that powers human respiration and cellular function. Now, glucose is a large, complex ring of carbon, hydrogen, and oxygen. It doesn't break apart into ions like salt.
So how does the water dissolve it without ripping it apart?
Because glucose is covered in those hydroxyl groups, oxygen bonded to hydrogen, which means the surface of the glucose molecule has the exact same partial positive and partial negative charges as the water molecules.
It speaks the same magnetic language.
Exactly. So when you drop sugar into water, the water molecules don't attack it and rip it apart. Instead, the water molecules recognize the magnetic handles on the sugar. They form hydrogen bonds directly with the sugar molecule.
Oh, wow.
They invite the massive glucose structure right into their tetrahedral scaffolding. They basically lock hands with it, weaving it perfectly into the 3-dimensional web.
So the sugar molecule is held in suspension, integrated into the water's own structure without being destroyed.
It is kept in solution. And this specific mechanical ability is why water is the perfect transport medium for biology. Going back to our initial statistic, we are 70% water. Our blood plasma is roughly 90% water.
Because it needs to carry everything simultaneously.
Right, because water can rip apart and carry inorganic salts, like the sodium and potassium. Our nervous system needs to fire electrical impulses and simultaneously weave complex organic sugars like glucose into its scaffolding to provide energy to our cells.
That's brilliant.
The water in our blood delivers the raw materials of life to every tissue in our bodies using these exact solvent mechanisms.
The very mechanics of dissolving sugar in a ceramic mug are the exact same mechanical physics keeping our brains functioning as we speak.
The microscopic physics dictate the macroscopic biology.
Okay, so we've established the relentless solvent power of water, whether it's through ion dipole forces ripping salts apart or tetrahedral webs holding sugars. I want to see this solvent power in action out in the wild. The research traces the journey of water through the environment, and it highlights a phenomenon that almost everyone listening to this has dealt with in their own home, probably without understanding the chemistry behind it.
The creation of hard water.
Yes. The research clearly differentiates between soft water and permanent hard water, and it offers a very practical household definition. Soft water is water that produces a good lather with soap. Hard water is water that does not produce lather, but instead forms a sticky scum.
It's the ultimate pragmatic test, isn't it? If you step into a shower and your soap foams up into a rich lather effortlessly, you have soft water. If you scrub and it just feels squeaky and leaves a film on the tiles, you have hard water.
Yeah, we've all been there.
But the fascinating part is tracing why that water became hard, because it is a direct consequence of water being the universal solvent.
So what does this all mean? The research outlines the journey. It starts in the atmosphere. It notes that rainwater, as it forms in the clouds, is naturally soft. It is essentially distilled, pure H2O.
But the second it begins to fall, it goes to work.
It does. The research states that while coming down, rainwater absorbs carbon dioxide gas directly from the atmosphere. It dissolves the CO2 into its molecular scaffolding.
It acts like a chemical sponge falling through the sky. And when water and carbon dioxide mix, they react to form a very weak acid called carbonic acid.
Okay.
So by the time the rain actually hits the dirt, it is no longer pure H2O. It is a mildly acidic solvent.
And then it hits the geology of the Earth. The research states that as the CO2-rich water passes through the beds of the soil, it acts on insoluble minerals in the Earth's crust.
Right.
Specifically, it attacks the solid rock. It chemically converts the insoluble carbonates of calcium and magnesium into soluble bicarbonates.
This is essentially a massive, slow-motion geological heist. You have solid limestone in the ground, which is calcium carbonate. It's hard rock.
And the research gives us the exact mechanics of this heist. We have the solid calcium carbonate in the earth interacting with the dissolved carbon dioxide gas and the liquid water. The weak acid attacks the crystalline structure of the rock. It breaks the bonds.
Right. It forces a chemical reaction where the insoluble solid rock is converted into calcium bicarbonate, which is highly soluble.
Meaning it dissolves perfectly into the water's scaffolding. The water literally chews the calcium out of the bedrock and carries it away invisibly.
It strips the earth of its minerals. And the research notes it does the exact same thing with solid magnesium carbonate, converting it to soluble magnesium bicarbonate.
So it's loading up on minerals.
It also dissolves chlorides and sulfates of calcium and magnesium as it percolates deeper into the aquifers.
And the research states clearly, these dissolved salts make the water hard.
Because once the water has aggressively dissolved all that calcium and magnesium from the bedrock, those metallic ions are locked securely inside the water's molecular web. They don't just disappear.
Right.
The water carries them into the aquifer, into the municipal pumping station, through the pipes under the street, and directly out of your shower head.
So the water hitting your back in the morning is carrying the microscopic remnants of dissolved limestone. But why does that ruin the soap? What is the chemical interaction between dissolved rocks and a bar of soap?
Well, soap is a brilliantly engineered molecule. It's amphiphilic.
Amphiphilic.
Yeah, it has a polar head that loves water and a long, non-polar hydrocarbon tail that loves oil and dirt. When you use soap in pure soft water, the tails grab the dirt on your skin and the polar heads grab the water.
Okay.
When you rinse, the water pulls the whole package down the drain. It lathers and cleans perfectly.
But hard water throws a wrench into that.
A massive wrench. When you introduce soap to hard water, the soap molecules never get a chance to grab the water or form a lather, because those dissolved positively charged calcium and magnesium ions in the hard water are chemically desperate to bind with the negatively charged polar heads of the soap molecules.
So the rock attacks the soap.
Exactly. The dissolved calcium instantly binds to the soap, neutralizing its charge.
Yeah.
The soap molecule is destroyed. It can no longer interact with water. Instead of dissolving into a bubbly lather, the calcium soap compound precipitates out of the water entirely, forming a sticky, solid, insoluble gray paste.
Soap scum.
Soap scum. The ring around the bathtub, the spots on your drinking glasses.
It is such a profound irony. The exact same solvent power, the polarity, the molecular tug-of-war, the electronegativity that allows water to transport vital nutrients through our 70% water bodies is the exact same chemical power that dissolves geological bedrock and prevents our soap from lathering.
It perfectly illustrates the central truth of this deep dive.
Yeah.
Water is never, ever truly empty. It cannot be passive.
Right.
By the time it reaches your tap, it carries a heavy chemical record of the atmosphere it fell through and the geology it seeped through. It is a product of its environment, shaped by its relentless interactions.
Which brings us to the final and frankly most sobering section of our deep dive.
Hmm.
We've seen water dissolve rocks slowly over centuries to create hard water. We've seen it transport glucose to keep us alive. These are gradual, natural, life-sustaining processes. But water's incredible reactivity can also be sudden, violent, and ultimately our species' biggest vulnerability.
Because a universal solvent is agnostic. It doesn't differentiate between what is helpful for biology and what is highly toxic. Its only imperative is to dissolve and integrate.
To illustrate just how extreme this reactivity can be, the research includes a detail that is quite startling. It sits in a little call-out box labeled "interesting information."
Oh, the cesium reaction.
Yes. It describes an interaction with an alkali metal. It states, if you add a lump of cesium to water in a glass trough, the reaction is so vigorous that the trough will shatter into small pieces.
I want you to really think about that visual. Think about the substance we bathe our children in. The calm, cool liquid we drink to soothe the dry throat.
Yeah.
If you introduce it to the right elemental trigger, in this case, the alkali metal cesium, the chemical reaction is so violently energetic, so instantly explosive, that the kinetic force shatters thick laboratory glass.
Why does it explode? Like, what is the water doing to the cesium?
It's a hyper-accelerated version of the tug-of-war we talked about. Cesium has one electron in its outer shell that it desperately wants to get rid of to become stable.
Okay.
Water, with its highly electronegative oxygen, is eager to interact. When they touch, the cesium instantly forces its electron onto the water molecule. This violent transfer literally rips the water molecule apart, severing the bond between the oxygen and one of the hydrogens.
It breaks the boomerang.
Yes. And when billions of water molecules are simultaneously ripped apart, they release pure hydrogen gas. The reaction generates so much instant thermal energy that the hydrogen gas immediately ignites into a massive explosion.
It completely shatters the illusion of water as this passive, calming backdrop to our lives. It is a highly reactive chemical agent. And that extreme reactivity, that incredible, relentless efficiency at binding with other substances is exactly what leads to the ultimate threat mentioned at the very beginning of the research.
This is what we call the pollution paradox.
Yeah.
It is the dark side of the universal solvent.
The pollution paradox.
Yes. The paradox is this. The exact same chemical properties that make water the perfect universal solvent capable of sustaining life, the polarity, the 104.5-degree hydrogen bonding web, are the very properties that make it dangerously efficient at absorbing toxic, human-made chemicals.
And the research spelled it out for us in the introduction. Post-World War II, the rapid production of synthetic chemicals, fertilizers and pesticides running off agricultural lands, heavy industrial discharge, the chemical leachate from waste dumps and landfills.
When an industrial pesticide is sprayed onto a field and it rains, the water doesn't ignore the pesticide. It doesn't flow around it.
He grabs it.
It treats the complex, toxic synthetic molecule exactly the same way it treats the calcium carbonate in the bedrock or the glucose in our blood. Its partially positive and partially negative magnetic ends grab onto the toxic molecules.
Yeah.
It pulls them into solution. It locks the poison right into its tetrahedral scaffolding.
And because it's locked in, it carries the poison straight down into the soil.
Right into the aquifers. Right into that 0.6% of the Earth's groundwater that we desperately rely on for our survival. And once those complex toxic chemicals are dissolved into the water, they are incredibly difficult to remove.
Because they're literally bonded to the water.
The water hasn't just carried them. It is bonded with them on a molecular level. Our municipal treatment plants are largely designed to filter out biological pathogens and basic sediments. They struggle immensely to break the hydrogen bonds holding on to modern synthetic chemicals.
And then we pump it into our homes and we drink it.
The research concludes that waterborne toxic chemicals pose the greatest threat to supplies, leading directly to waterborne diseases, especially in densely populated urban areas.
Because our bodies are 70% water.
Exactly. When we ingest polluted water, our internal solvent, our blood plasma, transports those toxic industrial chemicals to every single cell in our body, just as efficiently as it transports oxygen and glucose.
The solvent power that gives us life is the exact same solvent power that effortlessly delivers the poison. That is the paradox. We are navigating a microscopic margin of 0.2% potable water globally, and we are actively, aggressively filling it with synthetic chemicals that the water is fundamentally, physically designed to absorb and retain.
It is a delicate, intricate biological system balanced on the absolute edge of a knife.
We have covered an incredible amount of ground today, plunging from planetary macrosystems down to atomic electron configurations. Let's trace the arc of this to pull it all together.
Okay.
We started with the jarring reality that while we are terrestrial organisms built primarily of water, our entire global civilization relies on a razor-thin 0.2% margin of Earth's inland fresh water to survive.
We explored how water's unusually high heat capacity, the way its hydrogen bonds stubbornly absorb solar energy, acts as a massive planetary thermostat, basically buffering the climate and protecting us from extreme temperature swings that would sterilize the surface.
We dove into the 4-degree density anomaly, realizing that the specific crystalline structure of ice expanding is the only reason freshwater lakes don't freeze solid and obliterate aquatic life every winter.
We visualized the polar magic of the molecule, watching it act like a swarming microscopic magnet to ruthlessly rip apart salts through ion dipole forces.
We unpacked the 104.5-degree bond angle, revealing how electron repulsion creates a complex, three-dimensional tetrahedral scaffolding that gracefully catches and transports organic essentials like glucose without destroying them.
We traced a raindrop from the clouds, watching it act as a chemical sponge, absorbing atmospheric carbon dioxide to become an acid that performs a slow-motion geological heist on the Earth's bedrock, resulting in the hard water that destroys our soap.
And finally, we confronted the violence of the cesium reaction, which illuminated the terrifying pollution paradox. The reality that water's absolute brilliance as a universal solvent makes it fundamentally susceptible to absorbing the industrial waste, pesticides, and fertilizers of the modern era.
It is a mirror of whatever environment it passes through.
You know, throughout this entire conversation, I've been thinking about that glass of water I mentioned at the very beginning, the one sitting on the desk. You called water an environmental ledger.
Yes, it never forgets what it has touched.
So I want to leave you, our listener, with a final thought to mull over based on the sheer mechanical reality of everything we've unpacked today. If water is the ultimate universal solvent, if it is constantly, relentlessly absorbing the gases in our air, violently ripping the minerals from our soil, and locking the synthetic chemicals of our modern age into its tetrahedral scaffolding, then a glass of water isn't just a simple, passive drink to quench your thirst, is it?
No, it really isn't.
Is it possible that every single drop of water we consume is actually a highly detailed, chemically encoded memory bank, perfectly recording the exact environmental history of every single thing it has interacted with since the dawn of the planet, right up until it reaches our lips? Think about that invisible history the next time you take a sip. Thanks for joining us on this deep dive.